So I'll start now. So
Yep.
welcome to the Reactive Transport Modeling tutorial session. My name is Kewei Chen. I'm a postdoc at PNL. Today I'm going to show you how to build a reactive transport model in Flotran using the biogeochemical reaction network that is developed from the Lambda theory. I consider myself as a hydrologist, so my tutorial will be most from the perspective of hydrologist. There are two major components in this tutorial. Things like it's a big jump from the micro scale to the rich scale. I will first give a brief introduction for Flotran. I assume like most of you are biologists, probably you don't know what is Flotran and what kind of problems Flotran can deal with. So I will first give a brief introduction to Flotran, and then I will walk you through the setting of reactive transport model in Flotran. So what is Flotran? So Flotran is a massively parallel reactive transport model for describing subsurface process. P here means parallel. Parallel is the most important feature of Flotran because it can be used for large-scale model simulation, and flow simply means groundwater flow, and tran means transport, including both energy and mass transport. There are multiple processes implemented in Flotran. For example, single-phase variably saturated groundwater flow or multi-phase flow. Multi-phase here means gaseous phase and aqueous phase. For example, the air and water flow in the porous media. These two processes can be simulated independently or combined with other processes such as multi-component transport or heat transfer. This figure showing the geological structure for repertory for nuclear waste, and this color bar represents the concentration of radioisotope of iodine. So Flotran can be used for the non-term simulation of chemical transformation, especially for a large domain. So with those process implemented in Flotran, it can be used for many applications. Here I list some of the applications. For example, it can be used to simulate the CO2 sequestration, CO2 storage, and also for the geothermal systems, calculating groundwater pH. And it can also be used for simulating the permafrost modeling. So permafrost modeling means Flotran can simulate the phase change among water, vapor, and ice. And it can also be used to simulate the redox reactions within hyperexomes or remediation. So if you are interested in one of those applications, you can go to the Flotran official website, flotran.org, or you can just search in the literature. Next, I'm going to show you some cases we conducted at our study site using Flotran. The first case is rich-scale flow and heat transport model. Figure on the left showing the model domain. As we can see, this is a pretty big model. This model is 60 kilometer by 60 kilometer, and the vertical is distance is 100 meters. And the figure below showing the geological structures for this domain. We use Flotran to run the flow and heat transport over the large domain, and this simulation is run using about 2,000 cores for a few days. So yeah, if we don't have the parallel computing capability, we cannot run a model in such large domain. And the animation on the right showing the dynamic change of river tracer, which is showing here by the yellow color, and also the temperature change over time, which is shown on the right, and the moving blue line showing the like dynamic change of the water level, and the red line is showing the like the temperature. This is like another case. So we also use Flotran to simulate the flow head and solute transport at river cradle. The schematic diagram on the left showing the river cradle. So for the river cradle model, we are interested in the hydrological exchange flow between the river water and the groundwater. And the animation on the right showing the dynamic change of the river tracer. We can see the river tracer moving into the domain when the like water level is at high stage, and it coming out of the domain when the river stage is low, like at the low elevation. And this is like a third case. We can also use Flotran to do like reactive transport modeling for column experiments. This column experiments is conducted by our collaborators. It look into the reactions occurring in the natural reduced zone in groundwater systems. So here I list a few like main kinetic reactions that is considered in this column experiments. For example, the dissolution of solid organic carbon and the aerobic respiration, and also the sulfur reduction and the precipitation of like element sulfur, and the animation on the right showing the concentration change of some typical species during the column experiments. So the oxygen coming to the column on the like from the like left, and that this like simulation like reach like steady state about like 10 days after that. We can see the concentration does not change that much. So we've seen like Flotran can do a lot of things. So why we choose like Flotran? Yeah, at least like a few of advantages of you like Flotran. First of all, it's open source. And the most important, it has like demonstrated performance on supercomputers. The plot on the right showing the like scalability of the Flotran, we can see the computation time like decrease almost linearly with the increase of number of cores. And also, Flowchart has like active support from like many sources. There is like well-documented online documentation, and you can also like check the, like the source code. It is updated like frequently. And if you have like any questions, you can just like send an email to the Google group, or you can post your questions there. So I've like talked a lot of like flow, head, and reactive transport. Here I will like give you like a basic idea of how like those processes are represented in the subsurface. So this figure showing the like the conception model for the porous medium. Rows like yellow circles represents the grains or matrix, which is composed by like many minerals, and blue color means the pore space, and the magenta represents the pool of water flow. As we can see, the water can only flow within the pore, and actually it's very difficult to calculate the velocity at the pore scale, as like Tim just showed you. And so here, like we use so since here like we are like focus on the like field scale like simulation, we use empirical law to, namely like Darcy's law, to calculate the average flow velocity across the domain. So here V means Darcy velocity, and K means like permeability. Permeability is a property of the like the matrix. It represents the capability of the like matrix to allow fluid to flow through. And the mu is viscosity. It is a property of the fluid. And delta P is the pressure like gradient. Darcy's law tells us the fluid will flow from the from a high pressure to the low pressure location. And for the heat transport, the conceptual model of heat transport is kind of similar to that of groundwater flow. The difference is heat can conduct through the matrix. So we use the advection dispersion equation to describe the heat transport in the porous media. T here means like temperature, and alpha is thermal diffusivity, and larger alpha represents like a stronger like dispersion, and V is Darcy like velocities. Larger like V like means like a stronger like advection. And for the reactive transport, like it means the like slow transport with reactions. As we can see, the equation for like reactive transport is kind of like similar to that for the heat transport. Like C here means like the species concentration. Like, one difference is we had one more term like I at the end. It represents the consumption or production of the species. If the I is positive, it means the chemicals is like consumed during the transport. If it's negative, it means it's produced during the transport. So here I'm trying to put all like this governing equation for this like process as simple as I can. But for Flotran, in Flotran, the governing equation is like much like complicated. If you're interested in how like all those processes are implemented in Flotran, you can go to the Flotran online documentation. So with those like basic concepts in your mind, next I will like show you how to set up a model in Flotran. So for Flotran, the model is configured through ask2 file. So so we call that ask2 as the input deck. This is convention, and input deck is defined using keywords. This is an example. The capital like simulation and N. This is keywords in Flotran. So in this like simulation like block, we can specify what kind of process we want to simulate. For example, if we want to like simulate the like variably saturated flow, we can specify that the mode is a recharge. It will use a recharge to describe the flow process. And if we also like want to simulate the heat transport, we can specify the mode as like TH. T here means like thermal, H means hydrologic. If we want also add the transport process into the flow, yeah, we can add like one more block, which is the subsurface transport. And the global implicit is a way of Flotran to solving those nonlinear equations. There are like other options such as like operator splitting to solve those like transport equation. So once we specify the process we want simulating Flotran, next we need to tell Flotran what is the model domain, what is the property, and how long we want like do the simulation, and what is chemistry information. So the keyword like subsurface, this block of subsurface include like all those information. So I will walk you through all those like keywords one by one. First is grid. So the keyword grid is like in Flotran, like it tells Flotran like what the model domain is. So within the like grid block, you can like specify. There are like other options for the keywords. For example, you can like select the type is structure, which means the grid cell in Flotran you said is cubic, and then the NXYZ means the number of like grids in each direction. Here, like 16, 16, 16 means there are like 16 grid numbers in each direction, and the keyword like bounds represents the boundary in each direction. So in Flotran, the default unit is meter. So here it means like in X direction, the boundary is at like 0 meter and 60 meter, and the same boundary applied in other directions. So for the material property, we can like specify like the information such as like the porosity, permeability, but today I will not like go through that, because we're trying to make the flow model like as simple as possible. We will focus more on the like chemistry like part. So for the like keyword time, we can specify the how long we want to do the simulation. The final time like is a keyword like to specify that. So here like 10 means 10 like y means 10 years. And we can also like specify the initial time step and also like the maximum time step. So the time step in Flotran like it's not constant. It dynamically change according to the convergence while like solving the nonlinear equations. So the chemistry, like the keyword. So within the chemistry keyword, we need to specify a lot of like information that is related to the like reactive transport. Here, like I show the I use the like calcite like dissolution as an example. So within the chemistry block, we need to specify like other informations with different like keywords. For example, the primary species. This keyword like is asking you to specify those species that can be calculated independently, like within like by like Flotran, and also in the like block of like secondary species. Those species can be calculated using the like concentration value of the primary species according to the equilibrium constant, because like those like reactions run like very fast. And also like we can specify the gaseous species, CO2 gas, and the minerals is calcite, and the keyword like mineral kinetics, we need to specify the calcite there, and we also need to provide the rate constant for the mineral dissolution and precipitation. And the keyword like database, we need to provide the database, we need to provide the path for the database. So Flotran had like a very complete database there. It's named like Hanford.dat. So it has like many like commonly seen like minerals defined like in that like database file. It also like contains some like commonly seen primary species, secondary species, gaseous species, and also those like equilibrium constants for those minerals. If you have like new like minerals, you can modify the database to add that into Flotran. So Flotran can also be kind of like supports like monotype kinetics for micromediated reactions. So this is the monotype like reaction kinetics shown below. So we can add as many like mono terms as we want, and we can also add the inhibition terms at the end. However, if we have like new kinetics developed, for example, the kinetics that is developed from the lambda theory, it uses like exponential terms. This is not included in the generic Flotran. So in this case, we have to modify the source code through sandbox module of Flotran. So sandbox is another like feature of Flotran. It allows like users to implement their own kinetics into Flotran, and once you implement your like kinetics there, it is integrated with other processes such as flow, heat transport automatically. So after that, after we specify the chemistry information, we need to specify like the initial condition in Flotran. So with the initial condition, we need to tell Flotran the species concentration, for each species at the initial state. And for the like boundary condition, the setting is similar to the initial condition. So the boundary condition means the species that the species concentration that come into the domain. So yeah, the format is similar to that to the initial condition. I will not repeat it here. So this is the conceptual model we will work with today. It's a 1D river water infiltration model. So in this, like the figure on the top showing the dynamic change of like water level, we can see the water level is at high like stage in the summer and is low stage in the winter, and below is infiltration is like conceptual model for the river water infiltration. The blue region represents the river water, and the yellow region represents the sediments. So the groundwater is flowing in the sediments. The flow direction actually, so in the river, the flow direction depends on the pressure difference between the groundwater and the river stage. So if the river stage is at the low elevation, so the groundwater is at the hydraulic head for groundwater is high. Probably the groundwater will flow in upward. So if the river water is at high elevation, the groundwater will like flow like downward. So in our like tutorial, we're trying to simplify our problems. We will not consider the dynamic change of river stage. We assume that the flow velocity is in downward direction and the value is constant. Which means we will not consider the impact of river stage to the flow direction. And also we assume the species concentration in the river and in the sediments are constant and homogeneous. Homogeneous means the species concentration does not vary over space. So this is like general like biochemical reaction equation that we will like consider. We will like simulate today, and in the like the below is this table showing the stoichiometry for like each species for different like organic carbon. This like table is derived from the lambda theory. Him like just show you on the like day 2. So before I move into the like tutorial session, I will like need him to briefly go over the lambda theory again, so that we can continue from where he left.
Thanks, Kewei. I have only one slide, and because the Kewei will be using the output of lambda theory as an input to his reactive transport modeling using Flotran. So as I explained this figure yesterday, here the number of compounds in the FTICL sample is too many. So for Altahama samples, 10,000 samples that has chemical formulas assigned. And therefore, one strategy we use is that we just, based on their cumulative distribution, this orange line there, top left, and then x-axis lambda, and then we divide this lambda into a discrete number of beans. So for example, we discrete them into 10 beans. Each bean contains like the compounds that have similar thermodynamic properties, lambda values. And the bean 1 to bean 10, they are characterized by different lambda values. So what we did here is that from each lambda bean, we derived average chemical formula. So average number of carbon, hydrogen, and so forth. And then use that these 10 representative chemical formulas as the group, as a metabolite that represents each lambda bean. And then bottom left, you can see that how they are located in the Van Crevelen plot. And then also I compared that how average lambda value from each bean can be compared from the lambda value derived from average chemical formula. So they are very, very similar, indicating that really this classification and then using lambda, the average chemical formula, really reasonably well represent real chemical thermodynamic properties of each compounds in each lambda bin. Okay, that's it.
Okay.
Kewei?
Oh yeah. So I will start from there. So this screenshot is the narrative that like him like show you on day 2 how to like develop the model using lambda theory. So after you run the tutorial, you will generate those like FBA models, which is named like being average, stoichiometry, oxygen. So first we need to download those like reactions. There are like 4 options. You can download them like different format. Here like we will use like TSV format for demonstration. So T means like TSV means tab separated like values. So once you download this file, you unzip it. There are like 2 files included in this like folder. So one is like in with like compounds, and the other is in with like reactions. So for in the like the compounds TSV file, it contains all those compound information. So for example, the first column, it is the ID for like different species. XCPD means means like the organic carbon, and the formula is in the column C. As we can see, yeah, there's like pretty long like formulas for like for DOC, and also like we have like other like species, ammonia, oxygen, like carbonate, hydrogen, and we are like so in this data set there are like 10 reaction equations, and also like 10 like organic carbons. Okay, yeah. Oh yeah, the charge. Yeah, I think we also need the like the information of the charge. So here like the for the DOC is like no charge, but for ammonia like is like charge is +1, and for the like carbonate is negative, and hydrogen like is like 1. For like other columns, we don't need that information. And this is like another file, the reaction TSV. So in this file, it contains all those like reaction equations for each dissolved organic carbon. So the first column, like A, it is the ID. It is ID for like each dissolved organic carbon. So and in the like column of definition, it shows the stoichiometry associated with the associated with like the name of the compound. So it does not show you like explicitly what the like species is. So you need to refer to the other file, the compound file, to get the like species name. So here, like I will like show you how to set up the Flowchart model in Jupyter Notebook. So Jupyter Notebook is an open source web application that allows you to create and share documents that contain like live code, equations, and visualization narrative text. This screenshot showing the interface of Anaconda. Anaconda is like a platform that like combines like a few like popular application for data science. Yeah, here we can see there are like 2 like Jupyter. Yeah, one is Jupyter Notebook and one is Jupyter Lab. So actually the function of these 2 are similar. Jupyter Lab is like an advanced version of Jupyter Notebook. It is like more interactive. It's like more integrated develop environment. But like it's like some of the functions I develop here is not supported by the Jupyter Lab yet. So today I'm going to walk you through the workflow using the Jupyter Notebook. So after you open the Anaconda, you click the launch, you will see the the directory for I prepare for you. So here we can see there are 3 folders and 1 tutorial IPy notebook. So the data folder it contains all those data I downloaded from the KBase narrative. It has the reactions in TSV format, and the folder pflowtran, it contains all those pflowtran simulation related files, and the folder source it has some scripts I wrote for those tutorial. So this is a screenshot for the notebook. We can see there are a few. In the top, on the top is menu bar. It has multiple functions. For example, in the file you can save or create a new notebook, or you can edit. You can edit, view, and you can explore those functions yourself later. And in the middle is the narrative text. So as you can see, this is kind of similar to the KBase narrative. You can write whatever you want in the in the notebook in the markdown format, and you can also insert the link, an image, and equations. And below is a code cell. So the code cell you can directly run the code. So notebook kind of supports Python or R. So all those code I wrote for this tutorial is writing in Python. As you can see here, in the first cell, you need to import those packages that is needed by the tutorial. Okay, so next I'm going to show you how to run the notebook. So this is the virtual machine. I will start from the, I think I better start from the, this is KBase narrative. Him just show you on Dame 2. So after you go through the narrative, you will create those objects. So today I will use this dataset for demonstration. As you can see here, the being average stoichiometry oxygen. If you click here, you will see. We can download this dataset, and we choose TSV. It takes some time to download. I think I can just skip this. I can show you what is the file is in the Birchbox. So after we download that dataset in TSV format, we need to put that in the data folder. Here, this is a dataset that's downloaded from the KBase narrative. If we, here we can see this. This is a compounds TSV file. We can open it. This is what I'm showing in the slides. It contains all those compound information. The ID is used in the reaction equation, and we can use this table to get the formula for each compound. And this is another file, the reaction TSV. Yeah, for each organic carbon, it has like equations listed here. So in this data set, there are like total like 10 reaction equations correspond to like each organic carbon. So once we like put the downloaded like data set in the like folder data, let me close the notebook. Start from the beginning. So to launch the Anaconda in so the in the VirtBox I like install the like Ubuntu like systems to launch the Anaconda. First we need to open the terminal and type in Anaconda Navigator. Here. This is the interface of Anaconda. To launch the GP notebook. Yeah, if you have any questions, you can stop me anytime. So yeah, I put all those files in the folder PNL Summer School Flotran here. Okay. It takes some time to load the notebook. Okay, I will skip the introduction part because I have talked about that in the slides. So like all those like cells you need to run. Yeah, those like cells start like okay. Although cells start like within, it means this is like code cell. You need to run it before you move on to next cell. So in this cell, like we basically import all those like packages that is needed in this like tutorial. And the first step is to extract the biogeochemical reactions from Tsv file. So here we need to specify the directory for this data set. Here is like this data set is in the directory of that data. And we also need to specify the Flotran like simulation directory and the compound file name, the reaction file name. And I write a parser to extract all those stoichiometry and the specific information from those Tsv files. And the extracted stoichiometry information will be saved in this file, the RxCSV. So we also need to tell how many reactions we included. Okay. Okay. Sorry, I just missed something.
Kewei, there was a question as to whether the link to the Jupyter notebook would be available later.
I think so. Yeah, because like the VirtualBox size is like per big is 10 gigabyte. So I put that. Yeah, I think we can like distribute the all those like files to the like participants later. Yes.
Okay, thank you.
Yeah. So yeah, after like we run the sequencing, we will generate the stoichiometry file. I can show you what the file looks like. Yeah, this is file. That is. I think I can like send you the link after the tutorial session. Yeah, because like it takes a long time like to download all those things. Probably you can like do it like right now. So here is like the stoichiometry information that is extracted from like the Tsv file. So yeah, the first column is just like I gave a name for each reactions R1, R2 to R10, and the stoichiometry for like each species. So for the DOC things like the DOC, the formula like is pretty long as you seen like previously. So here I just use the DOC 1, 2, 3 to represent like each DOC. That is like included in each like reactions. So once we have this file, next, which is probably the most important step. So next, as I told you like before, so the kinetics like that's derived from the number theory that is not like implemented in like generic Flotran. So first we need to like modify the source code and to implement that kinetics by our like selves. So for this step, we need to provide like the file name. Yeah, here I name it like reaction sandbox PNL cyber. This is the photo file. It's an F19. And we also need to provide the stoichiometry information, which is obtained from like the first step. And we also need to provide those variables that are considered in the kinetics derived from like lambda theory, and also provide like units for each like variables. After that, we can like run these like functions to generate a Fortran source code that can be compiled by like Flotran. Yeah, also like since like all those like Fortran source code is printed out as streams using the Python code, probably there is some like format issue. So here I use another like I use the like f like file to formulate those Fortran code. This is another functions. I have installed like before like the after I install like before the like tutorial, and after like we have generated the Fortran like source code and format it, and we can like compile like pflowtran. Yeah, this is a command that can be like run in terminal. You can see this is just terminal bash command. Yeah, this command, it tells is copy the generated like sandbox like source file to the pflowtran like source directory. So the generated like pflowtran like pflowtran like source file is put in the pflowtran folder, and it will be copied to the this is like source file for the entire like pflowtran for the like pflowtran. It will be copied there. After that, you need to like compile the pflowtran. Oh, we need to run this first. Yeah, after you run this cell, yeah, it will like show you, yeah, the file is generated, formatted. So at the beginning of the compiling, it will give you a hint. This is the process of compiling like pflowtran. After pflowtran is compiled like successfully, yeah, it will show you recompiled successfully. So what is like Fortran file looks like? I will show you. Yeah, here. Yeah, this is like the Fortran like source code that is generated with Python script using all those stoichiometry information and the cybernet and the like kinetic parameters. Yeah, as you can see, yeah, this is a module that's named the Reactive Sample Cyber class, and it contains all those like species information. Here, like I use like DOC 1 to 10 to represent the each like species of organic carbon. This is a pretty long file. Yeah, here. Yeah, this is like the variables that is unique to our kinetics. We also need to provide this. Just forget what would be the zip file, but it's in like the So yeah, the zip file only contains like VirtualBox. You need to like enter the like VirtualBox, and all those files are there. The verb was closed before any attempt to power it on. Yeah, I'm not sure what's the reason for that. I can come back later after like I walk you through all those like notebook. Yeah, this part is to like specify those like parameters. Yeah, and also the name for like each species. Yeah, you don't need to understand all those like Fortran code, because it takes like probably it would take some time to learn like the sandbox. If you are interested in this, you can go to the Flotran of your website. If you go to the here. If you are interested, you can go to the. Oh, I can show you the. Yeah, this is a Flotran website. The source code is in the bitbucket. It's put in the bitbucket, and it also has some instructions on how to install Flotran. So if you want to learn the how to implement the kinetics in the sandbox, you can go to the source folder. Yeah, so here Flowchart provide some yeah, this is the source code of Flowchart. They're all in this directory. Here. Yeah, this is the source code. If you go to the reaction, yeah, all those files start with reaction or related to the reactive transport. So yeah, those files that start with reaction sandbox are related to the implementation of sandbox. There are a few kinetics already implemented in Flotran. For example, reactions in CN, and this is the cybernetic model. And I think if you want to learn, you can start from this file, the reaction sandbox example. Yeah, there is a detailed instruction on how to implement your own kinetics into the Flotran. So at each subroutine, there is the comments that tells you what you need to specify in that subroutine or module. And there's also another many other sample problems provided with Flotran. For example, if you go to the short course, yeah, there are many different problems. Yeah, you can just choose the problem you are interested in. For example, the corporate chain. Yeah, this is the input deck. You can start from there. Since the Flotran can be used for many applications and many different problems, yeah, it's very difficult for one to understand all those process or all those applications. So you can just start with those problems you are interested in. Yeah, also there are some sample problems for one hot steam injection, tracer injection and variable saturated flow. Okay. After we have generate the source code and compile it successfully, we can move on to set up the 1D color model. This schematic diagram showing the model domain. So it's 1D, and the origin point is at the bottom, and the the positive, like the direction is upward. So here, like we are the top river, we assume like the river is at the top side and bottom is like groundward side, and the flow direction is from top to bottom. So for the model domain, we need to tell Flowchart how long the model is and what is the grid dimension, because like Flowchart will calculate those like all those information like pressure, temperature, and species concentration, like based on like those like based on those like grids. So it will like give you like all those values at center of like each grid. So you run this cell. Yeah, it will ask you to provide the grid dimension in meter. So the default value I said is like 0.01 meter for each grid, and the total length for the column is like 1 meter. And next, we need to specify the flow velocities. Yeah, the unit for the velocity is meter per hour, and the direction is like downward. After we set the flow, set up the flow, next we need to specify the like reactive transport like condition. First is the initial condition. Yeah, we run this cell first. Then I will like. So here, like we make some simplifications so to make like the settings kind of similar to what like him like show you in the K-based narrative. Here, like yeah, there are a few assumptions I will like I need to like talk about first. First, we assume all those like dissolved organic carbon has the same like initial concentrations, and also yeah, and another thing like I need to like mention is, so in Flotran, all those like dissolved like species such as dissolved organic carbon and oxygen, that is mobile. So which means it can move with the water flow. But for the biomass, yeah, it's immobile. Yeah, which means it can only like be produced or like be consumed or like degrade at like the like and like the original like the location, it cannot like move with the water flow. This is like a different. It's kind of different from like what like him like simulate in his model. And also like yeah, the unit is different. So for those like dissolved like species like the oxygen uses, default like unit is molarity, which is like more per liter. But for the biomass, it's in different like unit. It's the more biomass per like cubic meter of bulk. Bulk is the like volume of the porous medium. You need to be careful for those like units. You can change those like parameters later, like when you like explore the like different like possibility of the model. So next is the boundary condition. Again, we run this cell first. So yeah, as I said, like the biomass is immobile. So here, like we only need to provide the like the feeding like concentration for like oxygen and dissolved organic carbon. That's enough. So after that is we run this cell. Yeah, this is like the formulation for the rate kinetics that is derived from like the thermodynamic theory. And we also like consider the cybernetic regulation. while I implement those in the sandbox source code. In here, the three parameters you need to specify: the harvest volume, the in liter, and also the maximum reaction rate per hour, and also the degradation rate. I assume the default degradation rate is 0. After we specify the kinetics parameters, next we need to set the time. So the default simulation time is 200 hours. And we can also specify the output time step, which means that the Flotran will save the outputs every 1 hour. So after that, we need to, after we have specified all those parameters in the Jupyter notebook, we need to generate a new Flotran input deck, because Flotran job can only be run through the input deck as shown in the presentation. So all those I provide a template for those for the Flotran input deck, and all those parameters you specify here will be inserted into the template and generate a new Flotran input deck. I can show you that. Yes. Yeah, this is the template for the Flotran input deck. Yeah, this is a process. Here we only consider the transport process. We make the flow field as simple as possible. So here we just assume the flow is constant. We can specify velocity. So here we don't need those process mode such as with recharge. Also, yeah. So in the notebook, we only specify the concentrations for the oxygen and dissolved organic carbon, but actually there are the other species. Yeah, that showing I was showing you earlier in the reaction equation. There are species ammonia, hydrogen bicarbonate, and we assume all those species are the concentration of all the species are pretty large, which means the reactions will not be constrained by those species. So because we in this tutorial we care about the behavior of the oxygen and the dissolved organic carbon. Yeah, this is the parameters for those Kinetic model. So after, this is a template for the Flotran input deck. And also, I provide a template for the this is I provide a template for the database, the species name and ion size, charge. You don't need to. So in this database, it does not contain all those dissolved organic carbon. So after you run this cell, it will add all those dissolved organic carbon into the template database. So here, if we run it, if we run it, this is like the generated Flotran input deck. As we can see, all those like derived organic carbon will be inserted here. And here is values for those like different kinetic parameters, K, mu, BH. And also the the velocity is specified here. This is primary species. Yeah, this is like model domain information. So since we only like do like 1D column model, so in vertical directions, so here we specify the number of grids in the x, y direction at 1, but in the z direction is 100. Because the grid dimension is 0.01 and total length is 1 meter. So the total number of grids is 100. Yeah, there are many other like keywords. If you're interested, you want to understand Flotran more, you can search those like keywords one by one in Google or in the like Flotran like website. But here I just want to like mention all those parameters that you need to specify in the notebook. Okay, here, this is the initial condition. Yeah, here. So for all those species, so the initial concentration you specified in the notebook will be inserted here. This is biomass. Yeah, as I told you. Yeah, the biomass is considered as immobile in Flotran. And this is like the constraint and the inlet, which is at the top. All those the physical meaning for those specific concentrations, like the concentrations in the like river water, and the physical meaning for those initial specific concentration is like the concentration in the groundwater. We can actually measure those values in the field, and both like for surface water and groundwater. Yeah, once we have that information, we can apply that in the like in Flotran. Okay, that is the end. So after you update the Flotran input deck and also the database, you can run Flotran in Notebook here. You can just click it. This window will show you the progress of Flotran running. It will take a few minutes to do the simulation. Here, so here, like this time tells you how long the Flotran has like. So it means the simulation has been run up to like 2.7 10 to the negative 4 hour, and the time step is 2.7 10 to the negative 4 hour. So the total like simulation time is 200 hours. Let me see how long. Okay, already like 77 hours. Yeah, probably we can like wait 1-2 minutes. Can finish soon. I think I have some demo. Let me see if I have like demo data set. Okay, yeah, I think I can use a demo. So after the simulation, like and Flowchart will put all those outputs in a Flowchart will like store like all those outputs in the format of H5, so we can read those like output file and see here. If you run this cell, we can see here are the like species like information. So we can visualize the species we are interested in. For example, the dissolved organic carbon. We can choose one. If we want like choose like multiple species, we press Control. Yeah, we can, for example, and we also need to specify the time point. We want to see the distribution of the dissolved organic carbon. For example, at 44 hours, we can like click. Oh, sorry. Let's see. This is just for. Yeah, if we. Yeah, once we choose the species and also specify the time, we need to run the next cell, plot the spatial distribution. Here we can see. Yeah, this is like showing the like spatial distribution for each DOC. And we can see here the reaction rate for different like species actually varies a lot. So for the like DOC1, it consumes much faster. This corresponds to the like being one in like his like he show you in his like lambda like in the lambda like theory like plots. And for the so at like the for the like dissolved organic carbon like 5, like if the reaction rate is much smaller, it's almost like constant, does not consume. And we can also plot the time series for different like species. Let me choose all those. Yeah, we can plot, or we can also like plot the time series at different like location here. Yes. Yeah, here is yeah, that's interesting. Yeah, increase at the end. Yeah, sound like species increase. I think probably I'm not sure. Probably he has idea of why it behaves like this. We can discuss this later in the. So we can like change those settings in the for different like parameters. For example, if we want like add the degradation, So whenever we change the parameters, we need to regenerate the Flotran input deck. We can see. Yeah, we can see the degradation rate is updated. So whenever you make any changes to the notebook for the parameters, you need to run the cell 3.5 again to generate the new input deck, and you need to rerun the Flotran simulation. Yes, this is what I have for this tutorial. If you have access to this, you can do it to your own. And if you are working on different data set, you need to place all those downloaded data set in the data folder and change the name. And also you need to change the number of reactions. For the second cell, yeah, if you do not know much about Flotran samples, I suggest you do not make any changes to this code cell, because yeah, if there's any typo in the Flotran source code, the Flotran cannot be compiled successfully, and you cannot run it. And once the Flotran is compiled successfully, you can make any changes to those. You can make any changes to all those parameters, and then you run the simulation and visualize the result to see how those parameters will affect the simulation results. But one thing I want to mention is, so if if you vary the so the default parameters that it can work, if you vary parameter a lot, for example, if you vary the velocity or the kinetics related parameters one order of magnitude or few order of magnitude, it is probably the Flotran simulation cannot converge. The time step will keeps counting, and it will take forever long to run the Flotran. In that case, you can just click the kernel and interrupt the simulation and start from the beginning, or you can just choose the restart and run all. Okay, I think that's what I have. Yeah, if you have any questions, you can ask me in the.
Hey, Kewei, thank you so much. That was really impressive. We do have some time for questions here, unless was there more of your presentation Kewei?
Yeah, thank. Hello. Okay.
Hi, still here.
Yeah. Oh, yeah. Sorry. Yeah. I didn't hear like.
So, did you have more for your presentation, Kewei, or is that it?
Yeah, that's it. It's what I have. Yeah.
Okay. Yeah, it looks like there was a lot of really impressive work, and really appreciate the demo. I think there was a little bit of confusion about whether they should be able to follow along with their own account on and link to the Jupyter Notebook setting and things like that. But we got that straightened out. Let's see. Let me go back and see if there are more recent questions. Great links to the Flotran site and how to get to the reaction sandbox.
So you want me to?
Are there?
Yeah.
So. Let's just wait and see if there are questions either coming in through Discord or on the chat. I believe some of the initial questions were mainly about how to access your notebook.
Yeah.
And
I can send you the link. I think, Ting, do you have the link?
Yeah, I do have the link. Is it, you mean to the Dropbox?
Yeah.
So I guess what I would say about that is, well, a couple things. I'm not sure, have we completely cleared that for public release or not?
Oh, okay, I understand. Okay.
Yeah, so we do have to go through our clearance process to do public release, but we can. I think we'll probably be able to release the Jupyter Notebook. The thing is, of course, to run all of these things, you'd actually have to have pflotran and Jupyter installed. So it's not a simple thing to just provide a couple files. The nice news is that these kind of approaches are actually being currently worked on to be built into KBase as apps. So as you've seen over the course of the week, using KBase is a very easy interface to use. And ultimately now we'll have the process be able to develop the Lambda models from the metabolomics and import them directly into a KBase app that can run pFlowtran. So that's really an exciting development. And as soon as that's available, that'll be something that'll be really easy to use. So people won't have to actually download and run pFlowtran on their own system, which can be a little complicated to do. So
there were some questions earlier. Excuse me, there were a couple of questions earlier in the presentation. One is, how would you upload the geometry into your setup? It looks like, if the geometry weren't a 1D column, are there more geometry boundary conditions that are available, or how are those incorporated?
Yeah, so actually pFlowchart has like a capability for to define like the model that with like either like structure like boundary or unstructured boundaries. So here like I just like consider like 1D model. So and it's in structure like grid. So probably we just need to specify the how many like grids in each direction and the boundaries for each directions. But pFlowchart can also support for like unstructured like grid if you are interested.
Yeah, there was quite a few questions actually about the grids and how you choose the grid resolution, whether you can do variable spaced grids, what kind of grid is it, a finite element, or I believe pFlowtran is finite volume if I'm correct, but
yeah. So for the like grid dimension, things like our problem is like pretty like it's just like small problem, just 1D. So we can like choose like a very small grid dimension. Here I choose like 1 centimeter. But if the like model domain is pretty like big, for example, as shown in the like presentation, probably we need to like increase the grid dimension. It depends on like your like computational capability. Yeah, if you have like more like computational resources, you can like choose a small grid dimension. Then you can like realize like you have like more information for the model for the like species, either species, flow, or heat transport at the specific like location in your domain. If you don't have like that much like computation resources, probably you can increase the grid dimension to reduce the simulation time. Yeah, it depends on your like on the model size and also your computation like resources, I think.
Mm-hmm. Kewei, can you comment a little bit on the benefits of using Jupyter Notebooks for setting up simulations like this? And if you know anything about it, one of the users was asking about, there's apparently a Python interface to pflotran called PyPflotran. Do you know about that? And if so, do you have any ideas of how that compares to, say, using it in Jupyter?
Yeah, so I think the Jupyter Notebook is very good for like demonstration purpose. Just you can say it's similar to the like K-based narrative. And yeah, I know there is like the pflotran, but I don't know if the pflotran is still like under development. I'm not sure because the pflotran is like there's like a few like major updates like every year. So when I developed the notebook like last year, this notebook it works at that time, but after probably like 1 month, 2 months, it cannot work because some functions does not like work, and probably we need to change some settings in the notebook to make everything like work like properly. If the pflotran is like keeps like development, I think that's a good choice. Yeah. I think the only issue is like pflotran is still like on development, and we need to spend a lot of time to make our like either like pflotran or the Jupyter Notebook to reflect all those like changes to pflotran itself.
Okay, great, thanks. Do you know anything about the timing or the
another question?
Oh, go ahead, Nancy.
Oh, I was just going to say there was another question along that line in terms of development of a GUI interface for pflotran, but it could be these Python interfaces, and Jupyter Notebook might actually take the place of that, or do you know, are there still efforts along a different interface?
Yeah, I know. Yeah, if we want to develop a GUI for that, probably it needs a lot of efforts because there are like many like options as you see in the website. They are like
sure.
Yeah, if you want like develop a GUI for that, probably it need a lot of time and a lot of effort. Many people to work on that problem. If you go to the documentation, you will see there are like many process, and in each process, like keyword. In each keyword, there are many like sub keyword. So if you want like put label,
Tim, can you talk a little bit, maybe if there's time, about the development of pflotran?
Sure. Yeah. So pflotran was developed from pflotran is a parallel version of a model called Flotran, which was developed at Los Alamos by Peter Lichtner, a serial code. And in the, let's see, it would have been, I guess, around the late 2000s that Glenn Hammond and Peter Lichtner got funding from DOE under the SIDAC program to develop a parallel version, high performance version of Flotran, which is now called P-Flotran for parallel Flotran. And this, so parallel Flotran, P-Flotran is able to run on the DOE's largest supercomputers efficiently using, I think they've run it on as many as hundreds of thousands of processors at the same time. And it can also run using GPUs, I believe, as well. So there's a number of advantages if you have very large problems, as Kewei alluded to. If you have a large problem and you want to use a high grid resolution and you want to include a lot of complex processes, you can chew up a huge amount of computer time doing that. So definitely running on high performance computers is important when you want to run those large kinds of problems. And so P-Flotran was developed under that funding source and became an open source code widely used now within the research community, especially in DOE, but also more broadly than that. And it continues to be maintained as an open source. I think Glenn is still the primary lead developer. And if you go to their GitHub site and their website, you can get engaged with the community and learn how to use and possibly help contribute to the development of P-Flotran.
So not seeing, I think there is more discussion going on the Discord link, but I think there seems to be a community answering those questions. Tim, what are your thoughts? Should we move on to the next talk? Young Sub, I think, has another presentation, or should we wait and take a quick break and come back at 11?
Yeah, I'm wondering if maybe we should just take a break and start again at 11 so that we don't throw off anyone who was planning to come to the 11 o'clock session. I suppose on the other hand, we might lose part of our audience if we do that. So what do you think, Hyun? Are you ready to go now, or do you want to wait until 11?
Either way is fine. I can go now if you want.
I suppose, what do you think, Nancy? Should we just move ahead with that? I don't see any real disadvantage to going ahead. We have 150 people online, so probably best to keep the momentum going.
I think it's also will be recorded, so if there are people that join, they can capture it. I think that would be a good idea. I'm kind of worried about the hard stop at 11:45. I don't want to make sure that we have enough time, and perhaps we can address questions if we finish early. So.
Okay.
Yeah.
That sounds great. Yeah, let's move ahead then. Thanks, Nancy.
Thanks, Kewei. I really enjoyed your talk. It was so informative.
Thank you. So I'll stop sharing.